Hello, hello. So this is like a mini summary lecture for the course TET 4180, Power System Dynamics and Control from NTNU. Lecturer is Kjetil Ulen, and prerequisites are some knowledge of control systems and electrical power systems. This will basically just go through my OneNote notes from the course. I've tried to structure it so it makes sense for me. What we're looking at now is sort of the final result, which are a few different models of the synchronous generator. So a second, third, fourth, fifth, and sixth order model. And these are like the main simulation models in use. The other chapters here are sort of the ones 1 to 11 here are sort of building up towards this final model, understanding where everything comes from and what the different terms and states here mean. The final part here is more high level. That's just frequency control. Will probably not be part of this video because it can be isolated. But I thought it's a good idea to look at the sort of final result before we dive into the details. All of these models have the so-called swing equation as the sort of main part. Very briefly put, how I understand it, the synchronous generator is a rotor, which is basically just a coil which rotates inside a armature or stator. And this rotor, it's driven by some turbine, so typically hydropower or steam or something like that. And this generates a mechanical power which accelerates the rotor. The stator or armature around the rotor, it has 3 coils. And in these coils, the rotating rotor generates some voltages due to electromagnetic effects, which we'll get to. At the same time, these 3 phases, they are connected to the grid. So yeah, I won't go into what 3-phase power is, but AC electrical power is usually transmitted in 3 phases, which are 120 degrees shifted for some reason. But these coils also have current flowing in them from the AC grid. So the stator coils also have some AC current. And this generates a electrical opposing force. So the rotor is driven by some mechanical torque. And the grid generates some opposing electrical torque. And when these are in balance, the rotor rotates at a constant speed. If the electrical power is reduced, so sort of this damping or opposing electrical power is reduced, then the rotor will accelerate. And if the mechanical power is reduced, then the rotor will decelerate. This delta here, that's called the power angle. And so when you have some DC current going in the rotor, generating some constant voltage, which rotates with the speed of the rotor, and the electrical opposing electrical power on the stator windings also generates a opposing torque. You basically have 2 forces which rotate with an angle. And the angle between these forces is the power angle. And of course, when the rotor accelerates, this angle increases, and when it decelerates, it decreases. And the swinging of this angle from this sort of steady state, that's sort of what the swing equation describes. And so section 2, or the first part here, is basically understanding this swing equation. So that's how this synchronous generator can be modeled as a mass spring damper. The mechanical power, it's fairly easy to model. It just comes from the turbine. The electrical power is a bit more complicated, and that's sort of the main focus. And if you look at these more advanced models, as I understand it, all of these sort of states, so for the most advanced here, there's 4 internal voltages. And all of them are modeled because they enable a proper computation of this electrical power. But there are simplifications which make this easier, and sort of models that ignore some of these effects. So that's the electrical power. And then usually there's some damping. And this damping can be just simply modeled as a linear damping, or it can be sort of implicit through the effect of these internal voltages on the electrical power. So to reiterate, all of these models, they have some mass spring damper swing equation. They have some internal induced voltages, and they have some electrical power. And this electrical power is just some algebraic combination of states, which is in part driving this swing equation. The reason these models are necessary is, for example, if you want to simulate this, what you would do is you can see if we just take the third order model here as a starting point, you have your speed deviation, which I guess you can initialize to 0. You can say you are in steady states. This power angle, this cannot be initialized to 0. It has some steady state lag for some operating conditions or powers. And finding that is an important task for initialization of simulations. So that's finding this initial power angle. And that also relates to this, whatever induced internal voltages you model, its initial condition will also depend on this power angle. So while chapter 2 here, or section 2 in my notes, describes just the swing equation, section 3 can be thought to describe how you can initialize this power angle and these internal voltages. Once you have those, you can solve this green area here that's related to if you have multiple components in a power network. You have to sort of describe something called power flow, so how currents and voltages sort of transfer over the network. That's not the main focus of this course. However, once you have done that, you have some currents and going from your generator terminals, and this current can be decomposed into a certain coordinate system which rotates, and the offset of this coordinate system is defined by this power angle. And then you can just step this model you have in a loop. So that's how you do the simulation. That was a very bad explanation. The main idea here is that if you want to model how the synchronous generator behaves to short circuits or different controllers, and you want to simulate it, then you need to initialize all these states, and that's the main part of this course. Yeah, you can see that these internal voltages, which define the electrical power, they have some differential equation which governs them. And that's because things change continuously after a disturbance. However, you can model these as being constant, at least for some time period. And this leads to a few nice techniques for steady state analysis of stability, for example. Final word is that you can see that some of these voltages have dashes, some of them don't. And that reflects something called the different transient states of the machine. And section 4 explains how they sort of originate. So this was just a very rough of where all of this is going. There is differential equations for the rotation of the synchronous generator, and then some differential equations for some voltages, because these define some electrical power, and this electrical power links to this swing equation. So that's just where all of this is going. So after that short, bit messy intro, we can actually start. So power systems, there's a few time frames of interest, and the fastest time frames are related to high voltage DC lines. So that's lightning strikes and switching effects and stuff like that, which is not really the main focus. Then there are so-called electromechanical phenomena. And this is the swing equation. So that's the rotating masses in the generators and motors. So that's very important. And then there are electromagnetic phenomena, which are changes in flux through the different machine windings after disturbances. Disturbances in this course are typically short circuits. And these two phenomena are the time frames which are represented in these models. So the electromechanical time frame, that's the swing equation. The electromagnetic time frames, they are these induced voltages and how these change. So going back, the slowest dynamics are related to the thermal dynamics in like steam power plants, and that's also not the focus here. The course is called Stability, Dynamics, and Control. So dynamics, that's these dynamic timeframes. Stability in power system is just being able to sort of return to your operating condition without oscillations. Stability can either be related to linear systems, in which case there's a lot of nice theory from control systems, eigenvalues and all of that, which you can use. All of these synchronous generator models are actually nonlinear. That's mostly related to the electrical power, but they can be linearized around some operating points. Just a brief note about control. So the way the synchronous generator is integrated to the grid is usually a turbine, which generates the mechanical power, and some excitation system, which defines the DC current going through the rotor. And this excitation control system is usually a voltage control system. So that's for voltage control and voltage stability. While the turbine, as you saw in the swing equation, the mechanical power drives this rotor. And so it's related to the frequency of the electrical energy. So frequency control is done through adjustment of the mechanical power, which is done by adjusting the valve for the fuel intake, while voltage control is done by adjusting the excitation current on the rotor. So those are the two control loops, and the frequency control loop is much slower than the voltage control loop. Before we begin, especially when it's coming to understanding this electrical power, there's some basic electromagnetism which is important to understand, and these are the equations of interest. So in like AC power, there is where you have inductors and capacitors, there's a generalization of the basic resistance, and that's called impedance. And impedance relates current and voltage through Ohm's law, which is that the voltage is the impedance times the current. And the impedance over a resistor is just a constant, so that's a real number, while the impedance over inductors and capacitors are complex numbers. So they include the frequency and they include the so-called inductance, this L, or the capacitance, this C. Inductors are the most important for synchronous generator analysis, and that's because synchronous generators are just a bunch of coils and inductors are coils. So the focus will be on inductors. Inductance is defined as N over R, where N is the number of coils. So the more coils you have, the more your inductance is. And it's inversely related to something called reluctance. And reluctance can be thought of as some sort of resistance to magnetic flow. When you have a current going through a coil, this generates some magnetic force. And that's called the magnetomotive force, or the MMF. And that's it's a magnetic force. And that's simply given by the number of coils times the current. There's something called magnetic flux, which I guess is magnetic flow. So it's the magnetic analog of currents. And that's given by this magnetomotive force divided by this reluctance. So there is some sort of voltage, resistance, current analog going on here. Then, if you have two coils which align, the force and flux through one coil can link with the other coil and generate the voltage in that coil. And that's the main principle for how synchronous generators produce power. So if you think about your rotor, which is a coil which is rotating in the synchronous generator, there is a current there, and this current is producing a magnetic force according to this MMF law and the flux. And as this rotates, it links with the 3 coils which are stationary in the stator and generates some voltage. And there's something called flux linkage, which is basically how much of this flux or magnetic flow through the rotor coil links with the stator coil. And that depends on the cosine of the angle between them. And since this rotates with the frequency omega, you have cosine of omega there. And also it's greater the more coils you have in the stator winding. If you expand this, you get a term which is like the product of the number of coils in one coil and the number of coils in the other, or number of loops, divided by the reluctance between them. And this term is called the mutual inductance. Finally, the whole point is that there's a voltage induced, and this is given by the negative derivative of the flux linkage. That's called Faraday's law. And yeah, so current through coils generates some magnetic force or magnetic flow. This can link with another coil, and then it will generate some voltage there, which induces a current. And these are the equations which define that, and all of this is important to finally arrive at the expression for power. So that's the mini intro to industrial electronics. Moving on, the next topic is power balance. So that's the introduction to this swing equation. So I've basically introduced this already, but there's a mechanical power which accelerates the generator, and there's a electrical power which dampens the generator. The swing equation itself is derived through Newton's second law. So you view this as a mass damper system where you have your difference between your mechanical input power and your electrical power, and they are accelerating or decelerating this rotor. I'll not get into the details there, but the swing equation is basically inertia times acceleration, or m times a equals force or torque. If you drew this in a block diagram, you would get something like this. So your mechanical power drives this, your electrical power breaks this, and you may have some damping and some inertia. And this generates your frequency deviation. And if you integrate it, you get your power angle. So what is this power angle? It's important to understand, because seeing as it's just the integral of the speed deviation, and I may actually break down a bit, because this I'll actually reiterate just what this delta omega here is, because this is not just the grid frequency. This is the deviation from the nominal grid frequency. So it's like some error coordinate. But the integral of this is this power angle, and since it's the integral of some speeds, you need to sort of initialize it somewhere. So which angle is it, sort of? And the way we can understand this is by taking a step back and considering just a very simple circuit where you have one voltage, one reactance, and another voltage. And reactance, just in case I forgot to say that, this product here, omega times L, that's called reactance. So reactance is basically just some frequency adjusted version of inductance. Okay, so you have a coil basically between some voltages. And the reason this setup is important is because the synchronous generator can be modeled as exactly this. It's just some voltage, which in this case is actually the induced voltage from the rotor, some coil, and then some sort of opposing voltage induced in the stator coils. And the power exchanged between these voltages, it's given by the product of the voltages times the sine of the angle between them. So, and this angle between them is called the power angle. So if we consider this diagram here, which may look a bit complicated initially, but it's actually fairly simple. This is a so-called phasor diagram. And so what you have is you have the voltage on one side and the voltage on the other side, and you can see that these are at a angle to each other. And this angle is called the power angle, and they're at an angle because inductors introduce a phase shift between the two AC voltages. So while a resistor just scales it up or down, inductors actually also shift this in phase. And what this says is that the active power exchanged between these two voltages, it's related to the sine of this angle. So what this means is that when these voltages are at 90 degrees to each other, then your power is maximum. The reactive power is related to the cosine of this angle, so that is maximum when they are aligned. So that's the basic understanding of electrical power. And this equation will be used once we are able to sort of model our synchronous generator as just some voltages separated by some reactance. So there's also a nice rule of thumb, and that's that active power relates to frequency stability in the grid, and reactive power relates to voltage stability. I have not personally understood completely why, but the main takeaway of that is if you mostly care about frequency stability, which this course does, we are mostly concerned about the active power. And so if we plot this active power between these two voltages separated by a reactance, it's just a sine function. And if you consider this plot, then you can see that some part of this curve is green and some part is red. And due to stability considerations, you have to remain, so your power angle has to remain in this green part of the curve. And some intuition for why that is can come if we go back to our simple swing equation. And we notice that here is this electrical power, this electrical active power, which is just the sine of this power angle times some constants, or actually not constants, but for now constants. And this power angle is here, so that's the integral of this speed deviation. You can close the loop by simply linearizing this sine function. And then you get some linearization constant or synchronizing constant. And you can, from control system analysis, you can tell that if this constant is positive, then this is a negative feedback loop, which is stabilizing. But if this constant is negative, if this gradient is negative, then this becomes a positive feedback loop, and this power angle will shoot to infinity. So that's sort of a impression of why this active power and how it relates to the power angle is important for stability of the frequency in the grid.